Hello, in this video, we are going to discuss the definition of generalized exponential function and the definition of generalized power function. In fact, we have already mentioned very briefly the exponential functions in topic 1.4 in the very beginning of this course. The exponential function has the form of a raised to the power of x, and we call this a to be the base, and x is sometimes called the index and sometimes it's called the power. So I'll call fx equals to ax as a raised to the power of x, and x are sometimes referred to the exponent or the index or the power. So to me, the power, the exponent or the index, they should be understood to refer to the same thing, that is the x that appears in the exponential function. The exponential function of a power x could be defined and understood from the basis of the exponential function. Here we call this the generalized exponential function. Here we just call this as the exponential function. The exponential function is derived as the inverse of the logarithmic function. I have assumed that most of you understood what this exponential function is and the properties that is associated with the exponential function. Sometimes we refer this exponential function as exponential function with a base of e. How would you define the generalized exponential function based on the natural exponential function? We begin the definitions of generalized exponential function from the inverse equations for e power x. We learn that e raised to the log of anything, log of a, is equals to a. Here, since a is the argument that goes into the definition of the log, and since the log function is only defined for x that is positive, therefore this statement is only true for any values of a that is real and positive. Then we would like to make use of another property of the exponential function, namely e power x1. When you raise it to power x2, this is the same as the e raised to the power of x2 raised to the power of x1. The first term here refers to the situation where you first obtained e power x1, then the result of e power x1 is raised to the power of x2. Whereas here you have e raised to the power of x2, then you raise the whole thing to the power of x1. And it is found that this is the same as e raised to the power of x1 times x2. That is, you take x1 and x2, you multiply them, you obtain a number, then you raise e to the power of x1 and x2. So using these very simple properties of the exponential function, let us try to raise the a to an power of x, where x is any real number. Okay, so let us try to do this. If you raise a to the power of x on the right hand side, you also raise to the power of x on the left hand side. That is what you do. So here you know that you have e raised to the power of ln a, then the whole thing raised to the power of x. Therefore, according to this theorem, this left hand side is the same as e raised to the power of what? Of x multiplied with ln a. That is, you take the log of a, you multiply with a number of x, then the whole thing it becomes the exponential to e. In other words, you calculate x multiply with ln a. After that, you raise e to the power of x ln a. And that is always possible because the exponential function is always defined. So this number can always be defined because the exponential function is always defined for all values of the index. In other words, you can always define the generalized exponential function a power x as the left hand side here. That is a power x for a that is real and positive, and x for any real number, whether it is positive or negative. You can always assign value to the a power x by referring to the exponents of x times ln a. So you define the general exponential function by assigning to it the values based on the definitions of the exponential function.